If we take a look at my fancy nomenclature review sheet, do you see anything about aromatic structures? No, it wasn't on that list. Okay, so where is it coming from? It's really just adding one extra set. We'll refer to naming our benzene structures, and our root name for that will be benzene. Really creative. Okay, so if we take a look at two possible structures in the lower left-hand corner, okay, well, if benzene is my root, for that top one by benzene, it has a chloro substituent. It becomes chlorobenzene. Where is the chloro substituent located?
1.
By definition, position 1, ignore that. How about the next one? Nitrobenzene. Okay. And I will try to reiterate the nitro, okay, but we need to remember some special characteristics about the nitro. Our Lewis structure. The really, really special characteristic about the nitro is that nitrogen is positively charged. Okay. The oxygen is negative. Can the oxygen act as a nucleophile? No. Resonance. There's a lot of resonance that negates the oxygen's nucleophilic ability. If we draw out the resonance contributor, what happens to the nitrogen? It stays positive, meaning that nitrogen will always be missing electrons, which means it is always withdrawing electrons from whatever it's attached to, okay? Which we saw when we were looking at Michael additions. Those hydrogens are now acidic because the conjugate base becomes, wow, stupid double bond underneath. Because the lone pair electrons can be stabilized by doing resonance out to that nitrogen. And even then, what charges the nitrogen? Still positive. So the nitro group is extremely electron withdrawing. Okay? It has a large contribution to how our benzene and, for that matter, other structures will react and interact. Okay? Why not? Let's make a slightly more difficult question. Let's combine those two. How would I name this compound? So what's our root name? What are our substituents? Why'd you not say the other way around? 2-nitrochlorobenzene.
For the halide, it's on all those.
It has to be in alphabetical order.
Unfortunately, it's alphabetical order. The priority of naming our functional groups is deciding which one dominates the name. So it's not chloro versus nitro as far as identifying that. This is going to come down to be 2-nitro, whoops, chloro 2-nitrobenzene. Is that what you said?
No, I did not say
You
that.
said it right. You didn't say it's 1.
No, I said 2-chloronitrobenzene.
Yeah. It becomes chloro 2-nitrobenzene. The chlorine comes first. It also picks up the first substituent.
So you have to do, the benzene rings, it's based off of alphabetical,
Yep.
not ranking.
Not the ranking. The ranking system, our priority of naming our functional group is what is our highest priority functional group in this structure. I'm going to name the compound. The suffix picks up that name.
So
Because chloro and nitro, both of those are substituents on a larger structure. They aren't going to contribute to the suffix. Benzene takes the priority there. You'll notice benzene isn't in my list of priorities. I'm going to say it's roughly equivalent to
Alkene,
why alkenes.
double bonds.
We're looking at carbon-carbon double bonds. As far as our priorities, it's probably roughly equivalent in there. Okay. Just as we saw for our alkyl groups, for instance, if I wanted to name this compound, what would I name it? accept a couple answers, and since you guys seem to be doing the correct one, 2-chloropropane, can't use. Come up with a new one. 2-chloro is going to be a bad way to start for the next name.
Does it have to do with methyl?
Give you an idea. That is the end of our name. No, not quite, but right idea.
Methyl chloride?
No. So where Chris was going was propyl chloride. That would be propyl chloride. It is isopropyl chloride. Okay. We had common names for certain functional groups. That shape is our iso because there's 3 carbons there. It's isopropyl. Okay. What happens if I had this structure? I have my iso shape, but I have 4 carbons, and it becomes isobutyl chloride. Okay. I know that was a long time ago, but it's kind of going to come back to bite us when we look at our benzene derivatives. For some benzene compounds, they are so common that, or so, yeah, common's good enough, that we refer to them not based off of our standard like nomenclature system, but we assign a new name to them. Okay? For instance, you already know one of them. Don't tell me benzene. Wait for it. That's phenol. Why are we not naming that according to our other nomenclature system? Well, number one, our other nomenclature system would be really confusing to name that. What, benzeneol? Okay, it's kind of weird, but that would be our standard kind of breakdown on it. Why do we refer to it as phenol? We've used it often enough that in its history, someone went through, named it phenol, and then refused to change their nomenclature system, and we're stuck with that. So we have other examples that do the same thing. I think Laura can help us out on this one. Toluene. Isn't it methylbenzene? Yes. Why do we call it toluene? Because somebody named it Bob, and now everybody has to name it Bob. Okay, that's the way it works. Okay, so there are several compounds like that: toluene, phenol, anisole, aniline, styrene, acetophenone, benzaldehyde, benzoic acid. Okay. Some of which you've seen, some of which you haven't. You're just kind of responsible for knowing them. Probably the more important ones: toluene, super common; phenol, super common; aniline, super common; benzoic acid is super common. Okay. The rest of them, I don't think I've ever seen styrene written out, okay, unless someone was doing a polymer reaction, in which case they were making polystyrene. Okay. Acetophenone, I think, was one of the unknowns. Did you have that, Corey?
I did.
So acetophenone is a fairly common one, but again, not typically used in our nomenclature systems. Okay? The ones starred in red tend to stand out. TNT is written there, and not TMNT. TNT. What does TNT stand for?
That's funny.
Anybody know what TNT is? Dynamite. T for tri. N, nitro, and T, toluene. Trinitrotoluene. You put 3 nitro groups onto a toluene, you now have TNT, and that's very explosive. Why? A lot of it has to do with those nitro groups. The nitrogen not wanting to be positive, you've now put a whole lot of that in the same area. If you agitate it appropriately, that compound falls apart rather rapidly, along with everything else in the nearby area. Okay? So if we had to draw that out, what do you think?
Are those strong? No. They would
So
just
start
be-
with our base. What's our base?
And with 3 nitro.
With 3 nitro groups. Where do I place those 3 nitro groups? How many places do I have available? 5, but I can only place 3 things on there. That's an interesting question. Where should I place those 3 things?
Yeah, it doesn't tell you.
Close together.
Doesn't actually tell us in the name TNT. Right? It is typically 2, 4, 6, meaning nitro, nitro, nitro. Okay. So when we reference TNT, we don't include the numbers. Any ideas why?
It's usually 2, 4, 6.
No, I would argue there's a different reason why we don't include the numbers. Talk to little kids about their favorite class. How many of them say it's mathematics? Oh, I wonder why. We tend to have this phobia of numbers. Why do we not include 2, 4, 6 TNT in the name? Everybody's going to freak out about the 2, 4, 6. What's that?
Anywhere you put the methyl group is still the same.
If you label it 2, 4, 6. Okay? But I could have put the nitro over here. That's going to be a different structure. Or I could have put that last nitro over here. So it's going to change the numeric arrangement of it. Okay. Why do we get 2, 4, 6 being the most common form of where we could place those nitro groups? That's a question that we'll ask much later on, or not much later on, but probably next week. Okay. Hopefully Wednesday of next week we'll start to talk about that. Okay. So that's the basics of our nomenclature. After that, everybody's favorite, spectroscopy. There's a bunch of signals that can show up for IR of aromatic compounds because we've got lots of possible bonds. Okay, you are really ultimately responsible for only 2 of those. Those 2 would be the C double bond C and the CHSP2s. Okay, those are the 2 that you're really responsible for. So you get your CHSP2s just slightly greater than 3,000, and then you get your carbon-carbon double bond showing up somewhere around 1,600. Okay. Usually it shows up as multiple signals. I actually have it remembered as 2 signals, okay, but I think there are typically closer to 3. But we usually get 1,600 and 1,450 are the 2 that I tend to remember. Okay. So those are the 2 that you're primarily responsible for. Are there a bunch of others? Yes. Okay. Much less responsible for those, but they are there. You can look in the 1,700 to 2,000 range. Okay. They are very small peaks, but sometimes they show up, and the number of peaks and their intensities can tell you something about where your substituents are located on the aromatic ring. So it gets you lots of useful information by looking there. Okay. By that same token, in that 690 to 900 range, okay, you can also get an idea of the substitution patterns. Right. Give you an idea of those. We've got 2 tables that could set this up. So if we look at the far right, table B, 2000 to 1667, they've got example patterns that you could see. Okay, so if you saw 1, 2, 3, 4 peaks, okay, all roughly the same intensity, that would suggest you have an aromatic ring with only 1 substituent on it. Okay. Or if you saw one with only 2 peaks, that would suggest you had a di-substituted aromatic ring, okay, where one of your substituents was located at the 4 position. Okay, how do I know P meant 4? There's some more nomenclature stuff that we haven't officially talked about. Okay, but para is 4. Okay, so we could look at those. Again, not easy to detect. Sometimes they show up, sometimes they don't. I mean, clearly. Then you also have the 900 to 600 range. You can again look at different substitution patterns generating different amounts of peaks. Okay. The problem with the one between the 900 to 600 range,
Fingerprint.
those are deep in the fingerprint range, okay, starting to reach at the level of accuracy of our instruments. Okay. So not so easy to interpret and can be overwhelmed with a bunch of other signals. Okay? But it's at least something to be aware of when we're talking about IR spectroscopy. Sorry, questions about that? Okay. The next one is in NMR spectroscopy. What this slide is getting at is probably the most important part of aromatic or HNMR analysis, is that if you see signals in the 6.5 to 8.5 range, you should be super, super excited for your HNMR, because that means you have an aromatic ring. And based on the substitution patterns, you will get very particular signal patterns coming out of it. And that's what this is trying to show. Okay? If we have two unique or two substituents that are exactly the same, and they are substituted directly across from each other, we only get two signals. Okay? In our carbon NMR, how many hydrogen signals would we get?
Well, it depends what that substitution is.
Nope.
If X-
They're identical. If X is equal to X, this is carbon NMR, what's in HNMR? You would only see one in the aromatic range. So maybe that's what you're getting at. We're only referencing for the aromatic structure. We'd get one signal in our HNMR. Okay. If we went through and looked at, again, two X's, but now dye substituted closer to each other in what is technically known the ortho position. Okay. What do we expect in the carbon NMR? Carbon NMR? 3 signals. In the, I don't know why 3 equal 3, carbon NMR. For our HNMR, okay, we'd have the hydrogen here and the hydrogen over here. We'd end up with 2 signals in our hydrogen NMR. Kind of make sense? Okay. You should be able to break that down for all of the other ones. Okay. That can help you analyze an HNMR relatively quickly, particularly on a multiple choice exam, because if you see a characteristic pattern for, say, XY, okay, that upper right structure, and you're given the HNMR, what do we see?
4 signals.
Nope.
Oh, the HNMR?
HNMR,
2.
we'd have 2 signals. It's a little bit better than that. What would those 2 signals do as far as their splitting? They each have one neighbor, which means I get 2 signals, and each of those signals splits into a doublet. We get 2 peaks. So I'd see a pair of doublets in the aromatic range, and I immediately know there's 2 substituents located on an aromatic ring on opposite sides. Okay? So a little bit of practice can go a long way for aromatic interpretation. Okay? Questions about that? So, the next part. I went through, you guys did the play pause it video. If you haven't done that, you should go back and do that, because that is going to get you points as far as a quiz goes. We've got 3 primary classes that we need to be concerned about: aromatic, anti-aromatic, and non-aromatic compounds. Okay? And based on your responses to that video and my own evaluation of the video, I did not spend a lot of time talking about anti-aromatic and non-aromatic. Anti-aromatic I touched on, non-aromatic I pretty much left alone. Why did I leave non-aromatic alone?
Because it's not aromatic or anti-aromatic.
We could do that. What's that?
It's just everything else.
It's really everything else. That compound. Aromatic, anti-aromatic, non-aromatic. How do you know it's non?
It's not a ring.
It's not cyclic. Still non, but it's a ring. We don't have the conjugated pi system. So our non-aromatics are pretty much everything else. If you get rid of double bonds, you're non-aromatic immediately. Okay? If you get rid of a ring, you're non-aromatic immediately. Almost everything we've looked at has been non-aromatic as far as its chemistry goes. We're now approaching this idea of aromatic and anti-aromatic. The aromatic one I spend most of the time on because that one dictates a lot of the chemistry that we'd evaluate. The anti-aromatic I tend to spend a little bit less time on because it is exceedingly tricky. Okay? Anti-aromatic structures are not stable. Okay, that was the example of our, it's a good thing I deleted all those slides, the cyclobutadiene. That structure was anti-aromatic. Okay, we're still cyclic. We still have p orbitals at every single one of those carbons. Okay, so rule 1 is satisfied. If we move to rule 2, okay, we have to look at the number of electron pairs. Okay, if we run under the aromatic definition, I need an odd number of electron pairs. Well, there's how many electron pairs? 2. So right away, I don't have to worry about the rest of the formula, all those other numbers. It doesn't match the aromatic rule. Okay, so it's not aromatic. It's not non-aromatic, which means it's not aromatic. It's anti-aromatic. Okay, an even number. We have 2. Okay, we can break those rules down into their corresponding patterns and how they were derived and later used in other situations. And that's where we encounter this 4n plus 2. Okay, or for our anti-aromatic, our 4n rule. Okay. We're referencing the number of pi electrons. How many pi electrons are in that compound? With 2 pi bonds, I have a total of 4 electrons. It's not referencing the number of pairs, it's referencing the number of electrons. Okay? So 2 pi bonds equals 4 pi electrons. Our Huckel's rule is saying that that 4 pi must then equal 4n plus 2. Okay? And if it matches Huckel's rule, the answer to solving that, because we can solve that, one variable, one equation, the answer to solving that for n must belong to the set of whole number integers, meaning 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? If we go through and solve this equation, what do we get for n? I would get n equaling a half. Does n belong to the set of whole numbers? No. Which means that solve didn't work. It's not aromatic. What if we tried the anti-aromatic solve? The number, 4n total pi electrons. Okay, so that means the equation I'm solving now is just 4n. What does n equal? N equals 1. If I solve for n, just divide both sides by 4 and I get 1. Does that belong to the set of whole numbers? Yes. That now validates anti-aromatic as the name of the compound. Okay? So we're trying to apply that kind of patterning within it. A lot of people get confused by the n and how that differentiates from the number of bonds or the number of pi electrons or the number of pairs of pi electrons. It's all kind of similar and all entirely different at the same time. It's going to come down to which part you associate the definition with easiest. Right? And just to make matters worse, I'm going to give you another one here in just a second. Okay? It looked like somebody had a hand. Yeah.
Why would you do the equation when you just, if it's odd number of electron pairs?
So odd number could work, okay, as a possibility, but we can run into other situations where it's not quite as obvious. Okay?
Do they have to have both rules to be, or?
Both rules must be satisfied, yes. Other questions on it? Okay, so if I just gave you a structure, you're right. I can pick whatever definition I want to memorize it. What if I don't give you a structure? For the system with 16 pi electrons. Aromatic or anti-aromatic?
It has 4, it's going to be even.
We don't know.
Maybe anti. Well, 4 pi electrons.
So Corey's come up with an interesting idea. We could look at the number of pi electrons. Well, how many electrons go into a bond? 2. 16 divided by 2 is try again, is 8, which is an even number of electron pairs, which would suggest anti-aromatic. I hadn't even considered that one. I was going to go through and actually solve it all the way out. I'd do 4n plus 2, try and solve out. The n would end up being equal to, I don't know why I did 12, it's 14. 14 over 4. I get 3.5, which does not belong to the set of integers, so it does not match Huckel's rule. So I would try it again with the other one, and I get n equals 4. That matches my anti-aromatic definition. Right. The last way to do it, which is typically common for 130 students, 2, 6, 10, 14, 20, 24, 28, 32. What did I just list off?
Isn't that the anti-aromatic numbers?
2, 6, 10, 14.
Integers of 4, just not
Corresponding to what?
corresponding to how many pi electrons there should be
4.
for an aromatic.
Yes. You could memorize the amount of pi electrons that are going to get you to an aromatic structure or an anti-aromatic structure. You might say, well, isn't that a whole lot to memorize? Probably not. Okay. Can I draw a structure with only 2 pi electrons? Yes. The video had an example of that. Okay. That one's relatively straightforward and easy to do. How about 6 pi electrons? Yeah. Benzene. Cool. 10.
Yeah.
A little bit harder, but I can pull that off. 14. What are we up to now? 14, 18. I'm increasingly becoming more and more difficult to draw in a larger and larger structure. The larger the structure gets, the more difficult it is for me to draw. If it's difficult for your instructor to draw, what are the odds you're going to get tested on it? Not so good. Okay? So you can memorize a variety of different stages within this. Okay? The odd versus even electron pairs, your 4n plus 2 rule, or the exact number of electrons that you need to find within the pi system. Okay? For either aromatic or anti-aromatic. Does that make sense? Okay, I'm going to guess by Jen's yawn that yes, it does. It's okay.
Well, I have a question, but I saw that it was on this slide, so I will.
Okay. So hopefully what you guys got from before, we had aromatic, we had anti-aromatic, and the next one was
None.
non-aromatic.
Why?
Okay, why which?
Why is that non-aromatic?
Okay, why is this one non-aromatic?
Because it's conjugated.
Well, it's conjugated.
Not at the top.
Is it conjugated?
It is conjugated.
Well, it's
No, it's
kind of
not.
conjugated.
It must be conjugated through the entire cyclic structure. Every atom of your ring must have overlapping p orbitals. Otherwise, it is not a conjugated system. Okay, our rule is fully conjugated. That third one is not fully conjugated because I have an sp3 atom in it. That kills it.
I guess I was just
And
thinking
it's
of
even
that.
too.
Okay, and it's even. But then it could have been anti-aromatic, which
Yeah.
was probably what you were going to argue.
Yeah.
Okay. It's still not anti-aromatic because it's not a fully conjugated system. Next one.
Non-aromatic.
This one's now anti. Why is this one anti and not non?
The hybridization of that carbocation.
Look at the hybridization of that atom now.
But
It's
it's no-
sp2, which means there's a p orbital there. And what could I put in that p orbital?
Not aromatic.
I can put pi electrons. I can do resonance through that by dumping pi electrons in, which then means I do have a fully conjugated ring with overlapping p orbitals. It does not say every atom must contribute electrons. It just says, do I have p orbitals at every single atom? Yes, I do,
Because you're missing a hydrogen,
because I'm missing a hydrogen.
whereas the other one.
The
had-
other one had 2 hydrogens. I couldn't have a leftover p orbital. Okay? So this goes all the way back to our hybridization theory. When we hybridize sp2, we hybridize 1 s and 2 p's. What's left over? An empty p orbital. And what can you put in the empty p orbital? Electrons via resonance. Okay? Rule 1 is valid. Rule 2, does it match Huckel's? No. We don't have an odd number, I have an even number. It's not aromatic, it becomes anti-aromatic.
There's two pairs of electrons.
Yes. Okay. And just to be annoying, let's throw in the curveball. If we actually look at this compound in a real world situation, it ends up acting non-aromatic.
Well, see, that's right.
So why? An anti-aromatic system has unpaired electrons, which makes it very reactive. Do our structures want to be reactive? No. So what does the structure do? It attempts to change its shape so that it is no longer matching one of those rule sets. Can it change the number of pi electrons it has? No. What can it change? Rule number 1, a fully conjugated ring with overlapping p orbitals. To be overlapping p orbitals, they must all be
SP2?
in the same plane. Okay? And with a ring shape, we might think that they would be forced to do that. Except what could I potentially do about the now red sigma bonds? I could gently rotate. As I rotate, what happens to the purple p orbital?
It's out of the zone.
It bends out of the plane, which then means rule 1 is no longer valid. It's now non-aromatic. Okay? And this is where I usually get really irritated with the subject, because we're trying to apply these rules to our structures, and then you're saying the structure just said screw you and does something else. Yes, that's exactly what I'm saying happens.
So is this like looking at, I don't know about, like how it chair flips or?
It gets back to the idea of chair flips. Okay? It's relatively limited in our chair flips because
Well, this one's,
we have pi systems that and ring structures which tend to limit
oh, okay.
that kind of rotation. Okay? But yes, it does get back to that idea. Okay? Interestingly enough, all anti-aromatic systems are going to try to do this. Guess what happens with the cyclobutadiene? It also tries to adjust its structure to become non-aromatic. Can it adjust much? No, because of that forced ring structure, the four-membered ring. Okay? Which then means it does not shift much, and it really does act as an anti-aromatic compound. But it can ever so slightly bend, so those p orbitals come less in the plane, and it starts to act kind of less true to anti-aromatic and slightly more to the non-aromatic. Okay? Really what we're trying to address here is that you need to be aware of the strict classifications. Don't look at the secondary features of how an anti-aromatic structure can just screw everything up. Okay? I just want you to be aware of that issue. The textbook will mention that with the structure that I probably, holy crap, just drew really well. Our cyclooctatetraene sure looks like it would match which definition? Anti-aromatic, we have an even number of pi electrons. That structure is now so large that what can the ring structure do? It can bend a lot. That bend and flex actually causes that structure to not be flat, but to actually be kind of U-shaped. Your p orbitals now no longer in the same plane. It invalidates our rule number 1, and it ends up being non-aromatic, not anti-aromatic. Those structural contributions are stupidly difficult to identify and find. Okay? If you encounter a question about aromaticity on the final, what you should do is look at your bulk rules first, apply, answer, move on. If you got time, come back and say, are they doing some weird, nasty structural thing to me? Okay? Answer probably is yes, they are, but cover your bases first, because you might be able to eliminate enough answers to make it a little bit easier to approach. Make sense? Next one. Non. But those, it's a conjugated system, isn't it? Not a ring. It invalidates rule number 1. Next one. Why is the next one aromatic? I only see 4 pi electrons. Why do I count a pair of electrons from the oxygen?
Can they do resonance?
Not technically in a p orbital. It's in an sp3 orbital.
They can do.
What do you do, resonance?
It can do resonance, which means that sp3 orbital starts to look more like sp2, which means the lone pair of electrons is really kind of sitting in something that approximates a p orbital. Okay. According to sp3, the oxygen is not in the plane. But if the oxygen says, I will sacrifice those 2 degrees of bond angle rotation to drop into the plane, now what happens? It becomes aromatic, because I have an extra set of electrons. If it is aromatic, what does that say about its stability? It is more stable. So what does the oxygen say? Sacrifice the bond angle, make it aromatic. Okay? So that's why we count those lone pairs. Last one. Why'd you say anti? We'd have 4 sets of pi electrons, which would be even, which would suggest anti-aromatic. Troy, you're shaking your head no. Why?
It's aromatic.
It is aromatic, but there's 8 pi electrons.
The lone pair on the nitrogen that has the pi bond is not in that p orbital that we're talking about, like with the oxygen.
Remember, on the oxygen, that sp3 atom could rotate ever so slightly into the plane to be contributed to the pi system. The nitrogen with the double bond, that lone pair, is located on an sp2 hybridized atom that is aimed 180 degrees away from the p orbitals and in the plane of the bonds that are already there. That was a bunch of structural mumbo-jumbo for ultimately saying you can't bring those pi electrons in. Let's just say for, almost push that a little too far, S and G, S and giggles, that we did do the rotation. Let's rotate those electrons up to get them into the pi system. What happens as I rotate those electrons up? The electrons in the pi bond then rotate out of the system. So at any given point, I can only contribute 1 set of pi, or lone pair electrons. I cannot contribute both.
The NH,
On an atom, sorry. So if we go up and look at the nitrogen up at the top, that's an sp3 atom. Fair enough, I can count those lone pair electrons, because what that nitrogen will do is adjust its shape so that that lone pair now shifts into the plane, and we get an aromatic system. Why do we want the aromatic system? It's more stable. Kind of makes sense? Okay, let's make one quick modification. Wrong pen. Aromatic, anti-aromatic. Far right again. I erased the hydrogen from the nitrogen and put on a lone pair and a negative charge.
Isn't all one of them just like the oxygen?
I can still only count 1 lone pair. It is still sp3 hybridized, but only 1 lone pair can be rotated into the system at any given instant. As soon as it is rotated in, where's the other lone pair? Outside the system, perpendicular to the plane of the axis. We don't get contribution from that. Okay? So as a rule of thumb when counting your pi electrons, pi bonds, count them. Or double bonds. Count a pi bond as part of the pi system. Lone pairs count only if the nitrogen at the top is not attached to the pi bond. The purple ones don't count.
Let's talk about the
I can count 1 lone pair on an atom that is sp3 hybridized.
you can't count them on
I can't count them on an sp2 atom. I can only count it on the sp3. Make sense? Okay? So hopefully you're good at identifying aromatic and anti-aromatic. Let's throw in a big curveball. Last one.
Oh, wait a minute.
What What do we think? So do I have a fully conjugated ring with overlapping p orbitals?
No.
Every single carbon in that ring
Oh,
is sp2 hybridized, which means rule 1 is absolutely valid. I do have a fully conjugated ring with overlapping p orbitals. Okay, so it is not non-aromatic. You get lots of negatives in this stupid section. So now the question is it aromatic or anti-aromatic?
Do we need to look at the lone pairs on oxygen?
So there's an interesting question. There are lone pair electrons on the oxygen. Should I be considering those at all?
No,
Why not?
they're not part of the cyclic ring.
They're not part of the ring. Okay? I will only count the electrons associated within the ring. The oxygen's electrons are outside the ring, don't count.
So then
I appreciate the braveness there.
But they're not in the ring.
You're saying 2 pi bonds, which is 4 pi electrons, which matches our 4n rule, which would say anti-aromatic. I don't know, nobody else has said it's aromatic, so maybe you're right. What do you guys think?
I would agree with John.
Is there resonance?
What do you mean is there resonance? It's nasty. You won't like it.
Did that get us a different answer?
Is there a resonance that gets us a different answer? Yes, absolutely there is.
And you could bring in one of those pi bonds from an oxygen.
Where would we expect the pi electrons in the oxygen to go? Or in that carbonyl? I heard to the ring, and I heard to the oxygen. Which way should they go? To the oxygen because? I don't accept that either. Oxygen is more electronegative. We would expect those electrons to go towards the oxygen because oxygen is more electronegative. Where would we expect the electrons in the bottom carbonyl bond to go? To the oxygen, which would then suggest there's still only 4 pi electrons in the ring. So what are you talking about, Mike? You must be an idiot. You're not thinking about this right. Is there another form of resonance? And I know, Troy, you might kill me on this.
The one you ripped me on earlier?
Close, but not quite. So what Troy had suggested as a possibility is we take the electrons that way. If I had done that, how many pi electrons would I now have in the system?
With the blue arrows?
With the blue arrow still going out.
We have 3.
I would have 3 pairs of electrons within the pi system, which would mean
It's aromatic.
aromatic. What is the problem with drawing this Lewis structure?
You still have 4.
Carbon won't take the electrons.
What's the problem with it, Troy?
The oxygen.
It's never going to happen. It's bad.
Never going to happen. The oxygen does not have its octet satisfied. You cannot draw an oxygen without its octet satisfied. That is inherently a bad structure. I cannot do it. I did hear a reference to, aren't there still only 4? What is the hybridization of the carbon with the lone pair on it?
SP3.
sp3 atoms with a lone pair. I can count the lone pair. So I would have 6 pi electrons. What would happen with the other one? Those electrons can go out. Still 6 pi electrons. Okay. But we said that can't happen. So go ahead.
I'm just confused because the resin, are you just showing resin structure on the purple arrow?
Just the purple arrow. Well, blue arrow now shown too. If you really want to be specific on that. Oh, yeah,
That's why I was and that's why.
There. Okay. Now are you okay?
Yeah, now there's.
Okay, that's fair. And that is absolutely a bad structure. Okay, any organic chemist watching this is probably screaming at me, why did you just show that? You should never show that because now students will draw that. So you will never draw that structure because that is a bad structure. That does not mean there isn't resonance. I know, double negative.
Still move the pi bond to the oxygen to.
If I move the pi electrons to the oxygen, though, the carbon becomes positive, and I don't have the electrons I need to become aromatic.
Can't you put?
I would still be anti-aromatic.
Can you do the double bonds in the ring to one of the carbons?
Sure.
Oh yeah.
Is there another way to move electrons?
Oh, bond to carbon. We were doing, or bond to.
I understand where you're going with that. That is our standard format. You're right. There are three ways we can move our standard format. We can go bond to atom, atom to bond, or bond to bond. We've used all of those. Is there another way? No.
Oh, radical?
What if I only split it this way? What's the result?
Enough electrons to satisfy the aromatic.
We still have 3 pairs of.
Do I have any conformal charges?
Well, the bottom carbon doesn't have that,
Whoops, sorry, yeah.
yeah. But it still doesn't satisfy the oxygen, right?
But we don't end up with a positive charge, which is the biggest issue within that. And it's that positive charge and missing the octet that becomes the problem.
But isn't octet there though, because of that other bond?
It would technically only have 7.
Oh. Yeah, I can see it.
So now how many pi electrons are there? 3 pairs, where one of those pairs is split across 2 carbons, meaning this compound is actually aromatic, or can at least become aromatic if I do a radical reaction on with it. And that is exactly what happens. This compound very readily oscillates between the structure shown and this structure. It is known as quinone. Those of you that have taken biochemistry, does quinone sound familiar? That is really unfortunate. Has anybody taken biochemistry? Maybe I should answer that. No? No one wants to step out on a limb there with that? Okay. Good. Okay. Quinone is one of our oxygen or our electron acceptors and donors in your electron transport chain in biology. Okay. So it actually transfers electrons, allowing us to generate ATP. How does it allow it? Through this radical mechanism. Okay. So, neat little functionality. I spent way too much time on that than I wanted to. That just happened to be a fun question that I thought was interesting. Why do we care about it? If we were going to compare the reactivity of pyridine versus pyrrole, how would we expect nitrogen to act typically? As a base. Okay. So let's start with that. Let's look at its base reactivity. Which of those would we expect to act as a stronger or weaker base? I can go either way with that.
I'm not sure. I know that answer.
To act as a base, what must it do? Right. Bases are acceptors of H+. So if we're trying to figure this out, maybe what we should do is, I don't know, draw it out. Thank you. I'll get to that in just a second, Corey. Well, gee whiz, Mike, that was dumb. You just drew the structure. Whoops. I left off that hydrogen. How does that help me understand what's going on with this? They both accept hydrogen. We drew them both accepting a hydrogen.
One of them has 3 pi bonds, the other one has 2. Nitrogen is sitting on the pi bond.
Remember, the big hint here, what did we just talk about? resonance and in particular its contribution to aromaticity.
It wants to be.
So
Is pyridine aromatic?
it's still yeah.
It's aromatic, and I appreciate where the answer to the next question, which was,
Still
it's still aromatic. Did we affect pyridine's aromaticity by having it act as a base?
no.
No. So does it care?
No.
No. Okay. What happens to pyrrole?
You lose aromaticity.
It started aromatic. How did it start aromatic? Aren't there only 2 pi electrons or 2 pairs? There's a lone pair on the nitrogen. Because that nitrogen is sp3 hybridized, that pair of electron contributes to the aromatic structure. Pyrrole starts aromatic. What happens if it accepts a hydrogen?
It loses its own good.
It becomes anti-aromatic. Actually, no. It becomes what? Non-aromatic. For it to become anti-aromatic, it still has to have a leftover p orbital. It doesn't have a p orbital. Okay. Which is favored, aromatic or non-aromatic? Aromatic, which means that reaction does not work, and we strongly favor the deprotonated state, meaning that pyrrole
It's less reactive.
is less reactive than pyridine as a base. Exactly right. Right? So by identifying something about what reactivity we're looking at, acid, base, electrophile, nucleophile, writing down the definition of what that thing means, and then drawing out the reaction, we can then evaluate the parts and the pieces that go along with that and draw conclusions about said reactivity. Okay? Which is of critical importance because that's the chemistry we're actually taking advantage of in the next unit. Okay? So if we went through and actually looked at it, we've got the arrow pushing there, we can look at the pKa's. The pKa of pyrrole's conjugate acid is 0.4 versus pyridine at 5.2. Which of those is more acidic? The 0.4. The smaller the pKa value, the more acidic that compound is. Okay? If it's incredibly small, does it want to form? No. We're going to favor our reactant states. Kind of make sense? Okay. Little foreshadowing. What kind of chemistry would you expect of the following molecule? Okay, there's an idea. We could do an addition. What type of addition would you be doing? We'd have to do nucleophilic addition because I need the negative to attack the electrophile. Fair enough. That's fair game. That could happen. Nucleophilic addition. What's going to be the issue that I'm going to bring up about saying nucleophilic addition for this?
Talking about aromatics.
We're talking about aromaticity, and in your discussion of the reactivity of this, you're not talking about aromaticity at all. What do you mean elimination?
I want to make another pi.
Okay, what type of elimination would you do? Nucleophilic elimination? So bromine leaves.
Hydrogen.
And the carbon would become positively charged. That's a positive next to a positive.
It's taken away.
So a nucleophilic elimination, whoa, eraser. Nucleophilic elimination or nucleophile elimination doesn't seem to make sense. I then heard hydrogen leaves.
It's taken out,
Gets taken, hydrogen is removed, the electrons go to our carbon, generating carboanion. We have a negative next to a positive, also known as a pi bond. Because hydrogen was eliminated from the structure, that hydrogen was eliminated as what charge? H plus. Define for me H plus without using the term acid. Shit. Don't use proton. Don't use hydrogen ion. Don't use acid. There, that's the one I wanted. We have an electrophile elimination. That's how the textbook has referenced that mechanism. Okay, we've eliminated H plus. Okay, we've done an electrophile elimination. Okay. And the result of that reaction would get us an aromatic ring, and all would be right and happy with the world. Okay? That is our next unit.
Yuck.
Okay? Everything that you are responsible for as far as it's minimally going to be 2 more lectures. I'm going to try to keep it to just 2 so we can spend the last week of review, but it'll probably sneak into 3 lectures. That is everything that we're going to talk about within the next 3 lectures. I'm like 90% certain on that. Everything next 3 lectures is right there on that one slide. Okay? So you are getting a bunch of reagents. What you should be remembering is what functional group goes on, and then you can kind of BS your way through potential reagents. Okay? You've got a bunch of kind of secondary reactions that you've seen already. Okay? We've got the Birch reduction, which we did vaguely talk about earlier in the semester, and then the last 2, which are just confusing, NAS and elimination addition. Why is NAS going to be potentially weird? What does it look like happened? Substitution. But what did we substitute with? An OH group. And what does an OH group act as? Or a nucleophile, which then meant the ring had to act as an electrophile. That's kind of weird. Why would an aromatic ring act as an electrophile? Doesn't it have a bunch of double bonds? And what do double bonds have? Electrons. More than likely, our aromatic ring should act as a nucleophile. The NAS in the elimination addition, the ring swaps its chemistry and becomes an electrophile, an electron acceptor. Or an electron acceptor, which is tricky to deal with, which is one of the reasons why they're the last things on there. Okay. The last part, the orange and purple, look at multi-substitutions within a ring. Running multiple of these reactions and stringing them together, what order and how we predict those reactions to go. Okay. With that, I have to end.